The velocity of the wave, the displacement over time, is something that we might be pretty familiar with by now. The intensity of a wave is a measure of how much energy it carries. We can use the idea of wavefront to describe where the wave is. The frequency of the wave determines its pitch, so whether it's high or low, right? Hi everyone. Today we're going to be talking a bit more about waves. So in this section, working with waves, we're going to be talking about how to talk about waves, how to refer to different parts of them, how to draw them, and different things that we might want to graph them. Things like graphing over position or graphing over time. So to start with, we're going to be talking about wave terminology. We'll be learning what all of these different terms mean and exactly what part of the wave they refer to. Now waves have a number of different properties that we can measure. That's why we need to know their names. So these properties have names that we aren't really used to. We can't really talk about the acceleration of a wave, for example, although we can talk about its velocity. If we can talk about the properties of the wave, then we can calculate useful information about the wave. Things like how much energy it's transmitting or how fast it's moving. To start with, let's talk about the wavelength. Now the wavelength of a wave is the distance between two repeating parts of the wave. So we can see in this diagram over here that we have two repeating parts of the wave going up and then down, and the wavelength is the distance between these two top bits. So this represents one complete cycle of the wave. Over one wavelength, this part of the wave goes all the way down and then all the way back up. So what would happen if we took the wave and we shifted it across by one wavelength? Well, the answer is that it won't look any different. Because the wave is a repeating pattern, if we shift that pattern across by one wavelength, the pattern will look exactly the same as before. Instead of this part being in this location, it'll be this part instead. The repeating pattern means that we just can't tell the difference. Now, how do we write this down with algebra? The answer is with this Greek letter called lambda. So its wavelength is a distance, the distance between two repeating parts of the wave, and so we measure it in meters, the SI unit for distance. So the wavelength of the wave can be very, very short, things like on the scale of atoms, or it can be very, very long. There are some waves, for example, which might have a wavelength of many hundreds of meters or even kilometers. So depending on the wave and how fast it's moving and what it's traveling through, its wavelength can be very, very different. Next thing we'll be talking about is amplitude. As we can see from this diagram over here, amplitude is the maximum displacement of a particle away from its rest position. So this is the amplitude of the wave. We can measure it by starting at the rest position and being displaced in the positive direction or being displaced in the negative direction. Either way, you're going to get the same answer because the wave is symmetrical around its rest position. So if the wave is graphed, then the height of the graph will be showing the displacement of the wave. And so that will show you the amplitude. Of course, sometimes waves are plotted with things other than displacement, but displacement is usually what's used. And so we can usually measure amplitude from a displacement time graph. Crests and troughs. These are particular parts of the wave as opposed to properties of the wave, and they're simply going to be points of maximum amplitude, a crest, and minimum amplitude, a trough. So in a longitudinal wave, that is, a wave where the particles are displaced in the same direction as the wave is moving, then they won't be called crests and troughs. They'll be called compression, where the particles are close together, and rarefactions, when they're far apart. Remember that a longitudinal wave is a wave where the particles vibrate in the same direction as the wave's motion, something like a sound wave, or a wave sent lengthways down a slinky. So the distance between any two troughs or peaks, or compressions or rarefactions, will be the wavelength, because each crest is identical to the previous crest and each trough is identical to the previous trough. Next thing we'll talk about is period, which is a rather important property of the wave. So a period is the time that it takes for the wave to move one wavelength. So it's the time it takes for a crest or a trough to move from here over to the next crest or trough. So it's a time, and we measure it in seconds, as you might expect. So during one period, the wave travels one wavelength, and that means that after one period, it looks exactly the same as it did as when it started. So the period is the amount of time it takes for the wave to travel a wavelength. Closely related to the period is the frequency. So the frequency is how many wavelengths pass through the wave every second. It's looking at, for example, the crests of a wave and having a fixed endpoint and counting the number of crests that go through that endpoint every second. So you would measure this in per seconds, or waves per second. Fortunately, because per seconds is a hard unit to use, we invented a new one. We measure it in hertz, where 1 hertz is 1 per second. That means that if a wave has a frequency of 5 hertz, then it means that 5 wavelengths go through a fixed point every second. So it's related to the period pretty easily. The frequency is 1 over the period. The other way we can say this is that it's the reciprocal of the period. So we can see that if the period is measured in seconds, then the frequency will be measured in per seconds, or hertz. The velocity of the wave, the displacement over time, is something that we might be pretty familiar with by now, given that we've already worked quite a bit on displacement. So we can talk about this in the velocity in 2 different ways. We can say it's wavelength over period, because this will be the distance traveled, the wavelength, over the time that it took, the period. But hang on, don't we have an equation for period? We relate the period to the frequency. That means that we can measure the velocity of a wave with the wave equation. Velocity equals frequency times wavelength. So if we know the wavelength and we know the frequency, we can figure out exactly how fast the wave is going. The intensity of a wave is a measure of how much energy it carries. For a sound wave, for example, very loud sounds will have a high intensity, very soft sounds will have a low intensity. So it's measured by finding the energy flow through a plane perpendicular to the velocity. Now, what does this mean? It means that if we have a wave traveling left to right, then we're measuring how much energy it brings through a little square plane like that. Make sense? So we're going to be measuring this in the amount of energy it brings over time per square meter. And the units that we use for this are watts per square meter. Now we'll be talking about wavefronts. Wavefronts are pretty similar to crests, but they're often used in different contexts to the context in which crest would be used. So when we think about a wave spreading out in, for example, a pond, we can use the idea of wavefront to describe where the wave is. A wavefront is the crest of a wave as the wave spreads out. So in the case of a ripple, the wavefront will be circular and it will spread out in all directions. We can sort of say that this wavefront is the location of the wave when we're analyzing how it moves. It might be straight. Waves on a beach are often seen as being pretty straight, just flat lines moving toward the shore. They might be circular, like in this example, or they could even be spherical, like a sound wave spreading out from a source of sound. So let's apply some of these terms to real-world waves, in particular sound. So the amplitude of a sound wave determines its volume and its intensity, for that matter. The frequency of the wave determines its pitch, so whether it's high or low, right? So in air, which is what we're of course all used to, sound travels at about 340 meters per second. Alright, so now that we've learned about all these different wave terms and ways to describe terms, we can go on to some practice questions to make sure you've got it all down.